Okay. So what I'm going to do is I want to kind of mop up a little bit about oxidizing and reducing reagents, and then sort of finish up some stuff that we didn't get to in ethers. So I'm going to probably live lecture all 3 days this week, and we'll start talking about free radical reactions, which is what was scheduled for today. We'll do that on Wednesday and Friday. So the first thing is in terms of oxidizing and reducing. So if we have a primary alcohol, we can oxidize that primary alcohol first to an aldehyde, and then oxidize that aldehyde up to a carboxylic acid. So in general, when you see the O with the brackets, it means that that's an oxidation reaction. And then, of course, we can reduce the carboxylic acid back down all the way to the primary alcohol. We don't have a reagent that stops at the aldehyde, but there's a way we could go from carboxylic acid to aldehyde if we needed to. And then for the secondary alcohol, it only can be oxidized then to the ketone, and the ketone can be reduced down to the secondary alcohol. A tertiary alcohol is when you try and oxidize it, you get basically no reaction, because you can't form a carbon-oxygen double bond. That'll give you 5 bonds. So tertiary alcohols can't be oxidized, but secondaries and primaries can. So these are kind of the oxidation and reduction schemes that we've seen. And so I want to talk first about the oxidation, then I want to go back and talk a little bit about the reduction. Some of these were in the video, some of them were in the notes. We didn't really talk about them in class, so I want to make sure we go back through those. Right. So in terms of the oxidation schemes, we can have strong oxidizing reagents, and we can have oxidizing reagents that are specific for just going from primary alcohol to aldehyde. But if we use a strong oxidizer, they will go from secondary to ketone, and they will go all the way up to the carboxylic acid. They would also react with something like an aldehyde. So those are the strong oxidizers, and they are things like KMNO4, chromium trioxide dissolved in sulfuric acid. That actually has a name. That's what's called the Jones reagent, or Jones oxidation. If you dissolve chromium trioxide, you can have potassium dichromate is another oxidizer. And then, for instance, with aldehydes will undergo this reaction to a carboxylic acid with just oxygen. It's slow. It's a slow reaction. But if you have aldehydes, if you have a really old bottle of an aldehyde, sometimes you can see that it's, at one point I think we had some downstairs that were half solid, half liquid. The half solid was the carboxylic acid. That's a solid because it can hydrogen bond. So you have to purify those aldehydes before you use them. But they'll also react with strong oxidizers. So with these, a lot of these reagents, what you can see is they're chromium 6+ reagents. The problem is their chromium 6 plus, and chromium 6 plus is toxic or carcinogenic. If you've ever seen the movie Aaron Brockovich, which is really about lawyers, it's not really too much about science. But the whole point of that movie was that some evil company was allowing the chromium 6 to go into the groundwater. And the chromium 6 was used in the pipes to fight corrosion. So when it got into the groundwater, it gave the people cancer. Sometimes we can use this as a color test. So chromium 6 is orange in color, and chromium 3 is actually green. And if you went back and looked at that movie, they show these ponds, these green ponds of the chromium 3. But environmentally, everybody's concerned about all chromium except chromium 4. You can buy chromium 4 at CVS and take it as a supplement. But if it's chromium 3, you could imagine maybe it goes back into the groundwater and somehow gets oxidized up to chromium 6. But they never showed the orange chromium 6. So that can be a test. If you think you have something in there that's oxidized, or you know you have an alcohol, I want to know if it's primary or secondary. Just add some chromium 6. It would immediately go from orange to green, and that tells you it's not tertiary. Now, if it's primary or secondary, then you've got to figure out, well, what reagent would I use next? You could actually, something very easy would be add a little sodium bicarb to it, a couple drops, and if it fizzes, it's the carboxylic acid. So these are the qualitative methods that we had to use to figure out identities of molecules or figure out functional groups before we had things like IR and NMR. So that's the usefulness of those. The KMNO4 is purple. Stop. Is purple. We're going to do this experiment in the in lab a couple weeks. And when it gets oxidized, it becomes MnO2, which is a brown precipitate. So we're going to see the purple color disappear in the brown precipitate form. So again, another potential test. So those are the reagents that we would use if we want to go to the highest oxidized position. Secondaries and tertiaries, or secondaries and primary, bless you, up to a carboxylic acid. If we want to stop at an aldehyde, then we have to use one of 3 specialized reagents. And so if you want to go from secondary up to, you want to go from primary to an aldehyde. I'll show you it will work on a secondary. If you want to go from primary to aldehyde, your first choice is what's called PCC, pyridinium chlorochromate. And so that's chromic CrO3, HCl, and pyridine. And pyridine is this heterocycle. That's pyridine. So that makes pyridinium, the proton protonates the pyridine, making it a pyridinium ion, and then the chromic acid and the Cl- or chlorochromate. Again, problem here is 6 plus chromium, toxic, pyridine, reproductive hazard. So this is not the greatest of reagents, but it was the one that was developed first. So what they kind of did was tone down the chromium trioxide by using pyridine. The second one would be to use SWERN. And the SWERN oxidizer involves using something like DMSO. Typically, we just use the names of these. If on the final exam they show up in their chemical form, I usually just put the name associated with them as well. So Swern is a little bit more environmentally friendly. It doesn't have any of the heavy metals. And then what's called Des-Martin periodate, which is also abbreviated DMP. That uses what's called a hypervalent iodine. And it's also environmentally friendly. And we used that a few years ago because we had an primary alcohol we needed to stop at the aldehyde. It worked really well, as long as you didn't shake it violently while you were extracting and have it spray stuff all over the place, which it did the first time we used it. So that's in somebody's notebook. Be very careful with stuff sprayed all over. So it's a relatively green reaction as well, or environmentally friendly. So the Swern and the Des-Martin have kind of taken over for PCC. But that will stop at the aldehyde. All three of those will still react a secondary alcohol to the ketone. So they still will do that reaction. But they're not strong enough to oxidize an aldehyde. So that's kind of the way it is. And if you're gonna do this synthesis in a pharmaceutical setting where you're going to eventually use that material as a drug, there's a certain number of steps that you have to be. This chromium can't be used within a certain number of steps towards the end, because you can never prove to the FDA or that you can get all chromium-6 out. But that was the one that was first developed. I'm almost thinking that's called a Corey-Suggs reagent. There was a professor at Brown when I was a postdoc, J. William Suggs, who was the guy who helped develop that when he was a graduate student. So all three of those will work. They have just that one focus, really, is to make the aldehyde. Okay. So I didn't go over those explicitly, but now I have. So that means they could show up on the next exam. Okay, reductions. Everybody okay with that? It's just remembering those reagents. Really, if you see PCC, Swern, or Des-Martin, they're making aldehydes out of primary. The rest of them will go oxidize all the way up. Now, as far as reductions go, we know that in terms of reducing those carbonyls, we used lithium aluminum hydride or we used sodium borohydride. But I wanted to just kind of go over the idea of there's three reagents that you can actually use that are all kind of complementary to each other. And they're really good when you have a ketone and an alkene in the same molecule. I mean, we don't do a whole lot with multiple functional groups, but we will. Because in real life, nobody does reactions on single multiple with a molecule with just one functional group in it. That's not exciting. So when you do this, you have to be careful that if you're trying to convert one functional group into another, that you don't react the other one with it. So for instance, for this aldehyde, if I want to reduce, I have three choices. The first thing I could use is either lithium aluminum hydride or sodium borohydride, and then my H+. Or I could reduce this with hydrogen gas and palladium or platinum metal catalyst. Another reagent that I can use is hydrogen with Raney nickel. So the difference between hydrogen with palladium or platinum and hydrogen with Raney nickel is a carbon-oxygen double bond is much more stable than a carbon-carbon double bond. And that's why, for instance, when we did their Grignards, if we formed the O-, it always wanted to bring the pair of electrons back down, kick something out to reform that very stable carbonyl. So carbonyls are more stable than alkenes. And so if you try to reduce a carbonyl double bond with H plus and H2, or H2 and palladium or platinum, the palladium and platinum is not a good enough catalyst to make that happen. So that will not reduce a carbonyl. So we need to search for a catalyst that's better. And what's better is Raney nickel. And Raney nickel is basically kind of a porous nickel. It's got a high surface area. Since the reaction occurs on the surface with the hydrogen gas absorbing there, the more surface area you have, the hotter it is as a catalyst. And so it will reduce the carbonyl. It will sadly also reduce the double bond at the same time. So if I reacted this molecule with hydrogen and Raney nickel, I would end up with the double bond and the carbonyl both being reduced. If I just use hydrogen gas, I would end up reducing the double bond but keeping the aldehyde intact. And lithium and sodium borohydrides are sources of what? H minus. So what's the H minus going to react with? Not the oxygen. The carbonyl carbon bonded to the oxygen. So the H minus is going to come in and add to that carbon. And so I'm going to turn that part of the molecule after the then H plus H2O step, I'm going to turn it into a primary alcohol. Does the H minus react with a double bond? A carbon-carbon double bond? No? Why not? It doesn't. It doesn't react with a double bond, but why?
Because there's not really a component that's that's positively charged or negatively charged. So it doesn't necessarily attack because there's not really a dipolar.
Yes.
On the alkene component.
Right. So this H minus has a delta positive carbon that it can react with. So that means in a CO double bond, that carbon is electrophilic. And what's an H minus? It's a nucleophile. So what's a double bond? Electrophile or nucleophile? A CC double bond. A nucleophile? Why? What? Because the pi bond is its source of electron richness. So a double bond is also a nucleophile. So the H minus can't react with the carbon because they're both nucleophiles. But with a carbonyl, the carbon is electrophilic because of the difference in polarity and the difference in partial charges. So that means it won't touch. H minus won't touch the double bond. So if I want to reduce the aldehyde and keep the double bond intact, I can do that. If I want to reduce the double bond but keep the aldehyde intact, I can do that. If I want to reduce both of them, I can do that. So these combinations of reagents give us 3 different methods for reducing at least molecules with carbonyls and with double bonds in place. So that was the whole point of that series of reactions. Okay. Is that everybody okay with that? Okay, let's see, ethers. So we didn't really talk too much about the physical properties of ethers, and so I want to go back and talk about what's important about ethers. And what's really kind of important about ethers is that they're mostly used as solvents because they really don't react well or at all with nucleophiles and electrophiles, and so they make great solvents. Since there's no hydrogen bonding in ethers, they make great solvents with low boiling points, which means that they're easily rotary evaporated. They're not water soluble, so they make good extraction solvents. And that's primarily how we use ethers. The chapter on ethers is really short because as physical properties go, they have fairly low intermolecular forces, lower boiling points, they're flammable, and they form peroxides. And so I'll talk about those because those are the most important physical properties to avoid: peroxides and flammability. So one of the things is that when we make a Grignard reagent, in your book you'll probably see more about the solvent. Those typically tend to be made in ether solvents because they're not soluble in hydrocarbons. They're not soluble in pentane or hexane or benzylic or benzene aromatic solvents. And so that's one place where they're used. The oxygen will bind to the magnesium and make it soluble. We've used them in lab to do extractions, and so we know that they're not miscible with water, and they have low boiling points, so that we can go ahead and we can evaporate them easily. The problem with them is, number one, they are flammable, and when you get to things like we use in lab, diethyl ether, its boiling point's only like mid-30s, and so its vapors form easily and they are very flammable. So in the lab, when we've used ethers, we've made sure that there's no flames. There was a time when we didn't have hoods for everybody, and we had a really bad problem trying to keep people from lighting their Bunsen burners while other people were pouring ether. We had to keep the Bunsen burners like in a bin, and then a TA had to stand in front of it so nobody could take the Bunsen burner until everybody was done with their ether, pouring out their ether, because we had, like in Faith's lab, those long benches with no hoods. This was the old building that's gone forever. And so the first thing we did was we made hoods so that we didn't have to worry about that. But we still have to worry about somebody lighting a Bunsen burner with ether in their hood. I mean, it'll cause a small fire localized to the hood, but still. Ether vapors tend to be heavier than air, so they tend to collect on the tabletop. So that if you were over here lighting something, you could catch the vapors and they would come back. And they would make a whoosh sound as the flame shoots back. I heard that once. I heard that once from a graduate student who was in my lab, a fellow graduate student. And I heard that sound, and then I looked and I saw orange light on the wall. It wasn't light, it was a flame. And he's like, can you get the fire extinguisher? Because I have a fire. And then I had to go over and move him because he was basically backed up against the fire extinguisher. And then the guy came from across the hall, and we put out his fire and handed him the fire extinguisher and said, good luck with the paperwork on this one. Because he had caught his hood on fire by trying to recrystallize something in a beaker, not even an Erlenmeyer, a beaker full of ether that he put directly on the hot plate. And so then it started to boil, and one of the little droplets went up and hit the flame, or hit the top of the hot plate and caught it on fire. And then he tried to move it off and sprayed everything all over. And so then he had to engage in some sort of cover-up activities, like going down and getting a big petri dish that was his water bath. Then no such water bath existed. And so in lab, that's one of my pet peeves is like, don't boil ether, don't heat ether, or don't heat ethanol on the hot plate without a water bath. That's the reason why, because I don't want to use a fire extinguisher here. I haven't had to yet. And I don't want to use it this year. Okay. So that's one of the problems with ethers. Ethers were primarily used, as anesthetics or anesthesiology materials, and their big problem was, flammability. You had to be careful of that. So they are very flammable. Sometimes you can cut down on that, like it's been suggested that maybe in the lab we should use T-butyl methyl ether. It doesn't have nearly as high a boiling point. It has an obnoxious smell, though. And it's been added to gasoline to help the gasoline burn better as an oxygenate. Like, we have ethanol gasoline. Some people have used TBME, this is terbutyl methyl ether, or TBME. Problem is, there's probably a ton of TBME somewhere in the earth, like underneath old gas stations whose tanks had leaked during some of those years. So I don't think it's used. I think it's either ethanol or nothing now. But we don't use that as an extraction solvent. And both of those are probably better than dichloromethane in the environmentally friendliness, because I think Sherwin-Williams has outlawed all dichloromethane in their products starting in a couple of years. And I'm working on trying to outlaw it in organic lab, but I'm not quite sure what I replace it with. Josh?
Was the quality of the pungent smell also used to say if there's a leak or not?
You could use that. Most of the time what they would do is just look for this in the soil, sort of extract out the soil and then look for the ether. They did a lot of that by IR, by looking for that ether, that CO stretch signature. So that's one problem with ethers. Good solvents, we just have to deal with the flammability. The other problem with ethers is that they can form peroxides. So what's that? Well, let's take our diethyl ether that we use in lab all the time. And diethyl ether can react with oxygen gas that is in its paramagnetic form. So when it's in its paramagnetic form, it has two unpaired electrons. Now we're going to start talking about these species on Wednesday, but typically when you have an unpaired electron, you have what's called a radical. When a carbon has unpaired electrons, it's a radical. And radicals tend to be reactive. Both radicals in chemistry, radicals in real life, they all tend to be very reactive. And for the radicals in chemistry, it's because you can't have an octet if you have an odd number of electrons. So they need to get an electron, or more likely, what they like to do is take a hydrogen atom with its electron away from a molecule, forming another radical. And that process is called abstraction. So in this case, what the oxygen does is it comes in, and I should use a fishhook here. So the fishhook arrow says 1 electron. I'm going to break that carbon-hydrogen bond and let the hydrogen go as an H dot, and then the carbon's going to pick up the unpaired electron, or keep its electron. So this isn't what we normally do, which is heterolytic bond cleavage with pairs of electrons. This is only 1 electron moving at a time. And so what we end up doing is we end up forming the ether radical and then what's called a peroxy radical. One more hydrogen and it's hydrogen peroxide. But right now that's a peroxy radical. And the problem is this is oxygen. I mean, we can't stop oxygen from doing this. There is a certain percentage of oxygen that is paramagnetic. If you've ever seen a demonstration where people take really strong magnets and they pour the liquid oxygen through it, that oxygen is attracted to those poles of those magnets because it is paramagnetic. So when we breathe in oxygen, we're breathing in these radicals, which can then go around our body and start grabbing hydrogens. And we'll talk more about that because we need systems that will stop that process from occurring. Or else the oxygen that we can't not have it or we die, but we don't want these oxygens going around and grabbing hydrogens from things like, I don't know, my DNA, my RNA. I mean, if it's going to mutate, what would I like? The superpower I would like to have most is like maybe the cleaning superpower. Cleaning laundry or dishes, one of those 3. But I don't think that exists. I think it's just going to mutate and something bad's going to happen. So we need to have systems in our bodies that actually stop that from happening. We'll talk more about that. In this case, what happens is my ether then pairs up, my ether radical pairs up with my peroxy radical. So it's kind of like the oxygen comes in, one end grabs the hydrogen, it spins around and couples, and that's what this process is called. We'll talk more about this on Wednesday, but when you have 2 unpaired electron species coming together, that's called coupling. And so we end up with a peroxide. Now we talked about organic peroxides when we talked about using like HBr and an organic peroxide added the H and the Br, anti-Markovnikov. And we had a mechanism where we split the ROOR group right in half and made 2 peroxy radicals. And hydrogen peroxide will do the same thing. The problem here is that I have now made an organic peroxide. And let's just say that if you were into, if your explosives 101 class would be, if you want to make molecules that are unstable and will explode, the first thing you want to do is make a solid that becomes a gas when it explodes, because then you have the greatest volume change. And you also want to add or embed a gas molecule into that. So every molecule that has a gas molecule in it, we have to be careful of. Peroxides, anything with an N-N bond, and anything with an NO2 group, because the NO2 can form nitrogen dioxide. So this is a solid, and so in the old days, if we went and got a bottle of ether and it was in a glass container and we saw a solid at the bottom, we left the room and went and said, there's an ether with solid in there, And then, I don't know, they would evacuate the building, or they would send in guys with big spacesuits on to take. I saw them walking with a bottle across the parking lot when I was in graduate school. I don't know why they just didn't put it in like one of those bomb containment things, but it was surreal. But this isn't a reaction that occurs right away. It's a longer term thing. So when you had a lab that hadn't been cleaned out for 20 years and you went in there and you saw an old bottle of ether, it was just like, no, I think we need to leave. So that's a side reaction. So nowadays you can say, well, what do you guys do to prevent that? Usually they add a molecule that will keep the oxygen, will react preferentially with the oxygen versus having it react with the ether. That's an antioxidant. They'll add to the ether. We have test strips so that we can dip the test strip in, and if it turns like, I think, blue, it's like, no, we're not messing with that. But most ether comes in the metal containers now, and the metal containers help fight the peroxides. If we do find it, we can add some iron to it, and the iron will kill the peroxides. So we have to be very careful of that. And it's not like it's going to super explode, but if you try and rotary evaporate ether that has peroxides in it, that means the round bottom that's on the rotary evaporator can explode. And in graduate school, that piece of that glass hit the guy across from me right here in his safety glasses, and they were true metal or true glass safety glasses, took a chunk out of it. It would have been very bad if it wouldn't have hit the safety glasses. So we have to be careful of these kinds of molecules. And last thing about peroxides is, so this is probably 15 something years ago. One of our former students was teaching at Riverside High School, which is up north, and called me and said, hey, we have a bottle of diisopropyl ether. And I just said, are you in the same room with it? And he goes, yes. And I said, you might want to leave. And he goes, well, it's just sitting out on the bench top. You might want to leave carefully then. And the problem with diisopropyl ether is I form peroxides from a primary alcohol. Radicals, we're going to find out that radicals, well, you already have found out, but we'll review. So a secondary radical is even more stable than a primary radical. So diisopropyl ether will form peroxides even faster. So if you found an old bottle of diisopropyl ether, I can guarantee it's got peroxides in it. So I just said, you need to talk to somebody about this, and you should probably not mess with it. Of course, he had a colleague that then decided to mess with it. And nothing happened. But he's like, well, I think the guy I teach with is going to try and open it up. And I'm like, well, that's the worst thing. Because these solid peroxides form on the lid, so that as you're opening them up, the friction or the mechanical wrecking of these things causes it to blow. And I said, well, okay, if he's hell-bent on doing that, make sure that he uses the hand he doesn't write with in order to open up the container. Because whenever you're dealing with stuff that could potentially explode, and it wasn't really a joke, I think it was real, everybody would always say, use the hand you don't write with, so that if you don't have that hand anymore at the end of it, you can still write. So.
If the lead's more than likely made out of metal or a stronger material than the glass, right? Wouldn't the glass shatter on the hand that you're holding the bottom with?
Well, that's why you don't grab it. No, you only grab it with one hand. You don't grab it with two hands. Sometimes we do reactions in sealed tubes if we want high pressures. And so that was always the thing, was when you took that, like if you did it in a microwave, if you take it out, always reach in and grab it with the hand you don't write with. But if we're safe, none of this matters, right? So peroxides, good solvents, low boiling points, so they make good extraction solvents. But you have to be aware that they're flammable, and that they form these peroxides. I would imagine that most of the 20-year bottles of ether are gone. Well, there might be a 10-year bottle in my fridge, but it's been in the fridge, so hopefully it's slowed down that reaction. But it used to be the glass bottles were the worst because they didn't have any liner to kind of combat. So when we found one of those, they pretty much said stay out of there and sent in the guys with the suits. So those are just a couple things. And this free radical mechanism by which we form these peroxides is our introduction into what we're going to do, our further introduction into what we're going to do on Wednesday. Okay. So that's ethers. Physical properties of ethers. So, do we know how to make ethers? I take my alcohol and I convert it to an alkoxide, and then I react my primary or secondary alkyl halide with it to do what's called the Williamson ether synthesis. So that I basically could add my group with 1 or 2 R's to the end of the alkoxide. And how do we take an alcohol and make an alkoxide out of it? What? If I'm going to deprotonate an OH, what base am I going to use? What? I could use an N-, a C-, or an H-. Right, N-, C-, H-. There is a reason for a little bit of the madness in terms of having these phrases like protonate the oxygen, because hopefully, they help you remember what to do there. So I can deprotonate directly with N-, C-, H-. I could also use sodium or potassium metal. And I know I mentioned that last week. So that's one way to make an ether, is by Williamson ether synthesis. The other method that we can use is to use alcohols to make the ethers. And there's going to be nothing new in any of these reactions. So this is review. Okay. I'll just tell you that ahead of time, so that if you're like, wait, this isn't review, it should be. Let's say that I reacted methanol and isopropyl alcohol together. And I'm going to react that with H+, and that H+ is probably going to come from H2SO4. And I'm going to make an ether. I'm going to make methyl isopropyl ether. What's the first step in the mechanism? Protonate the oxygen. Which one?
The one. Okay.
Sure. We can. So Protonate the oxygen. Which one? Either. Okay, your choice.
The one on the right.
Okay. Now, either means you could do either the left or the right. You're going to get two different mechanisms. So you've chosen the one on the right. We will write that mechanism. Okay, so that's fine. They chose the other one this morning. Means if you find them, you'd find both mechanisms. So I'm going to form this oxonium ion. It's going to protonate the isopropyl alcohol, OH. What happens next?
Water.
Water leaves. Do we agree? Okay. Then I get that carbocation. What happens next? Remember, what's my goal? To make an ether. So what happens next? Josh?
The oxygen, one of the lone pairs from the C3OH will end up forming with the carbocation.
So in other words, the methanol will come in and attack the carbocation. The methanol being a weak nucleophile. Okay, so I'm going to end up with now this. And then final step, let's lose the H plus to form the methyl isopropyl ether. How would I classify that mechanism? SN1. Why? Because it involves a carbocation. Okay, so this would be the SN1 mechanism of forming that ether from those two alcohols. What would the SN2 mechanism look like? So let's say I protonate the CH3OH and make a CH3 with the two H's attached to it and make that oxonium ion. So let's say I protonate the one on the left first. Actually, it's methyl. It's a methyl. This is it would have to form a methyl carbocation for the water to leave. And methyl carbocations are even more unstable than a primary. So that water's stuck there. So what would happen next? If I can't do SN1, I've got to do SN2. So what's my nucleophile going to be? Remember, my goal is to make this. So what's going to add? And so that's going to have to come in, add to the methyl group, and kick the water off in an SN2 reaction, including an SN2 transition state. Oh no, we're out of time. Yeah. I don't think think this is going to work out with what I'm going to say next. So we need to have a take-home quiz problem. And the take-home quiz problem is to write both of these mechanisms with the transition states, the intermediates, etc. Look, you've already got one done. All you got to add is the transition states. Okay, so that's the first part of the take-home quiz, is to write both of these mechanisms, the SN1 and the SN2 for these two molecules, with all the transition states, etc., including the SN2 transition state, which, remember, has to look like this, trigonal bipyramidal. But, okay, then the second step, the second mechanism would be, imagine that I took methyl isopropyl ether, and I add now two equivalents of HCl to it. And those two equivalents of HCl are going to make methyl chloride and isopropyl chloride, and there's going to be a water molecule in this process. There are two different mechanisms for this reaction. And I guess what I mean by that is that there's actually one mechanism, but that mechanism has two parts. So I've got to protonate the ether oxygen, and then I've got a Cl minus left. And then after I get those two products, I've got another HCl that needs to react with it. This is called acid cleavage. So I would like you to write a mechanism. There's two possible mechanisms. But write a mechanism that gets me from that ether to both of those chlorides. And that's your take-home quiz. Your take-home quiz for Wednesday. Okay. And then if there's anything to talk about here with cleavage, we'll talk about that. And then we'll go into free radical halogenation, which is chapter 16, I think. So I'm straightening out the Canvas site tonight so that the reading assignments are up to date. And so you'll have that for Wednesday.